In this video, we introduce the concepts of collision theory and activation energy to help explain the effect that changing temperature has on the rates of chemical reactions. We already know from earlier videos that the rates of chemical reactions depend on collisions between reactant particles, and more specifically, the frequency of collisions, the orientation of those collisions, and the energy of those collisions. We also know that rates of reactions are temperature dependent and that the rates of most chemical reactions increase with temperature, and that a general rule of thumb is that rates will double with every 10 degrees Celsius increase in temperature. The temperature dependence for rates of chemical reactions actually manifests itself in the rate constant. If we consider a typical rate law expression, rate equals the rate constant K times the concentration of A raised to the power of 1 times the concentration of B raised to the power of 1, then we can see that if the rate of reaction is affected by temperature, then the rate constant K must be temperature dependent, and it actually changes with temperature. Now, you may recall that when we introduced rate constants earlier, we said that the rate constants were only constant for a particular reaction at a particular temperature. The introduction of collision theory is one of the simplest models used to explain the temperature dependence of reaction rates and why rate constants vary with temperature. The central idea of the collision theory model is that molecules must collide in order to react. The greater the number of collisions per second, the greater the reaction rate. However, we should also recall that not all collisions between reactants lead to chemical change. In fact, only a very small fraction of reactant collisions actually lead to product formation. This means that an increase in collision frequency is not enough by itself to ensure rapid product formation. It turns out that reactant molecules are required to come together in an appropriate orientation and with enough energy so that chemical bonds can stretch, bend, and eventually break to allow the formation of new bonds. Collision theory therefore encompasses collision frequency, the orientation of collisions, and the energy of collisions. It is a theory that assumes that, for a reaction to proceed, reacting molecules must collide with an energy greater than a minimum threshold energy and with a proper orientation. The minimum threshold energy that must be overcome for a reaction to occur is called the activation energy, EA. The magnitude of the activation energy varies from reaction to reaction and has the units of joules per mole of reactant. The notion that molecules must possess a certain minimal activation energy in order to react was first proposed by Swedish chemist Svante Arrhenius in the 1880s. He understood that energy is required to break and form new bonds, and that this energy comes from the kinetic energy of the colliding reactant molecules. If the colliding molecules are moving too slowly because of insufficient kinetic energy, the electron clouds will repel each other and the molecules will simply bounce off each other without any chemical change. If, however, the reactant molecules collide with enough energy at the correct orientation, there can be enough overlapping of electron clouds to allow rearrangement of electrons leading to the bond breaking and the new bond formation that's required to lead to new products being formed. Now, we've seen this reaction before. These coloured balls actually represent the reaction between two nitrosyl chloride molecules to produce two nitrogen monoxide molecules and one chlorine molecule. What's interesting here is this structure, which can almost be considered an intermediate structure between the separate reactant molecules and the formation of the product molecules. Such a structure is called an activated complex, and at this stage of the reaction is said to have reached its transition state. At this point, the activated complex can either break apart to reform the original reactant molecules, or, with appropriate bond breaking and bond forming processes, the formation of products will occur. The progress and energetics of a chemical reaction can be plotted on a chemical potential energy diagram, otherwise known as a reaction coordinate diagram. This is a potential energy diagram for the general reaction between two reactant molecules A and B, forming the products C and D. Although it could just as easily represent the reaction we just looked at, the decomposition of nitrosyl chloride to form NO and Cl2. So, on the left-hand side of the diagram, we have our two nitrosyl chloride molecules correctly oriented so that the two chlorine atoms are aligned, ready for collision. And on the right-hand side, we have our products. In the middle, we have our activated complex structure, where the dashed lines represent the breaking of nitrogen-chlorine bonds and the formation of new chlorine-chlorine bonds. Of course, this bond breaking and bond making cannot occur to any significant extent unless the energy of the reactant molecules is high enough to overcome the activation energy barrier. This represents the minimum energy required for a reaction to proceed. The magnitude of EA determines how fast a reaction will occur. If EA is relatively large compared to the energy of reacting molecules, then fewer molecules will have sufficient energy to reach the transition state, and the reaction will be slow. If EA is relatively small compared to the energy of the reacting molecules, then many molecules will have sufficient energy to reach the transition state, and the reaction will be fast. The final thing to note on this diagram is that, for this particular reaction, the final chemical potential energy of the products is actually higher than the initial energy of the reactants, and we say that delta H, or change in enthalpy, is positive. This means that, for this particular reaction, a net transfer of heat from the surroundings is required for the reaction to proceed to any significant extent, and indeed the decomposition of nitrosyl chloride is typically carried out at higher temperatures. When there is a net transfer of heat from the surroundings in a chemical reaction, we say that the reaction is endothermic and that the delta H value, the change in enthalpy, is positive. This particular reaction coordinate diagram shows the energetics for a generalized reaction A plus B going to C plus D, where the chemical potential energy of the products is lower than the energy of the reactants, and we say that delta H, or change in enthalpy, is negative. This means that for this type of reaction there is a net transfer of heat to the surroundings, and we say that the reaction is exothermic. We are very familiar with exothermic reactions. For example, the combustion of natural gas, or methane, gives off considerable energy to the surroundings, with the reactants of methane and oxygen having a higher chemical potential energy compared to the products of carbon dioxide and water. Arrhenius noted that the rates of chemical reactions tend to increase exponentially with temperature, and we have already noted that for every 10-degree increase in temperature, the rate of reaction doubles. The change in rate with changes in temperature is largely associated with a change in the value of the rate constant K. For most chemical reactions, the expression that best describes the relationship between the rate constant and temperature is given by the Arrhenius equation, K equals A times e raised to the power of minus EA divided by R times T, where E is the base of the natural logarithm with a value of 2.718 to 4 significant figures. EA is the activation energy with units of joules per mole. R is a constant known as the universal gas constant with a value of 8.314 joules per Kelvin per mole. T is the absolute temperature measured in Kelvin, and the symbol A is called the frequency factor or pre-exponential factor and is related to the frequency of collisions with the correct orientation. The importance of the Arrhenius equation and its practical use is the subject of the next video in this series.